All right, well, let's get started. Welcome to today's webinar. It's the first webinar of the fall training season for us here at WestGRI and SFU. My name is Alex Razumov. I am the research support specialist at Simon Fraser University, and also I am the lead of the national visualization team. And also in the room we have Marie-Hélène Bill, who's going to teach a number of webinars this fall as well. So today's webinar is going to be introduction to the visualization contest that we launched on Friday. And I'm going to show you lots of demos, lots of examples of how I load things into a little bit Python, but mostly ParaView, and how to process data in ParaView. So if you don't have any experience with ParaView, this is actually a good place for you because I assume no previous knowledge of ParaView. I will try to go very slowly. So let's jump into it. Last Friday, as you probably heard, we launched the National Visualization Contest, Scientific Visualization Contest. And the website for this is, I'm just going to paste it in the chat, is visualizethis.netlify.app. So here are the notes for today's webinar. I just pasted it in the chat. And if you click on this website, and then from the notes, if you click on Visualize This or on the menu items, that will take you straight to the visualization contest website. So who are we? We are the Alliance's National Visualization Team. So currently, team has 9 active members, and these people are support staff for, well, regional local support staff at different universities across the country who provide support to researchers in advanced research computing and high-performance computing, and they also have interest in scientific visualization. So they're a member of this national team, which has been around for about 12 or 13 years now. And here's a website linked from the for the team, link from the notes and from the contest. And if you click on gallery, for example, that will show you the typical visualizations that we help researchers with. So if you have any visualization questions, please reach out to me, reach out to the team, and we'll be more than happy to help you. But let's talk about today's contest. So we launched the contest on Friday, and we've been running this contest since 2016. So now it's in its 6th year, and from these notes, we actually have links to individual contests. So here I included the pictures from the previous contest that we ran in partnership with IEEE. So it was an international contest in 2021, and so here are a couple of nice images from the winning submissions. So really spectacular visualizations that we saw there. And I could give you, if you follow these links, you can actually see some really nice visualizations from previous contests. So why do we run these contests? So one of the things that, as I mentioned, we provide is visualization support. So we would like to tell all Canadian researchers about our visualization support and tell you guys that you can actually contact us, and any help that you need, we just an email away. And also, so there are a number of popular and open source visualization tools that we're trying to teach and popularize. So some of them I mentioned today, some of them I will not show today, but we teach these tools, and these tools are incredibly useful because they will let you analyze and render your data, in 3D, in 2D, whatever you want, and pretty much anything that you want to do visualization-wise. Now is accessible via open source tools. For me, the main reason why I actually run this competition myself is I would like to see novel visualization ideas from you guys, because we have these tools that are fairly that are amazing, that are but they're fairly standard in the sense that these tools provide some techniques, some filters to do things, but then what you can do with these techniques is actually completely up to you. So just going back to the example from the previous contest, so here is an idea of, here was a numerical simulation of the Earth's mantle convection, and one of the submissions, what they did is instead of showing this mantle convection in spherical geometry, they unrolled it into the flat weighted projection, where now you can actually have a sense of up and down. So if you have a rising plume rising from the core to the core mantle boundary, then it actually goes up in the visualization, and then the descending blob or plume goes down, and it's really amazing. So I would have never thought of doing something like this, even though I can do it fairly easily. But ideas are really what you can do is really limited by your imagination. So who can participate in this year's contest? the answer is essentially anyone. So we are primarily targeting graduate students and postdocs from Canadian universities, so early career researchers, but we don't really limit visualization contests to, just that subset of researchers. So if you are a professor, for example, if you're a high school student, you can still participate. We'll be more than happy to see your submissions. A couple of words on contest terms. There's actually not much there. So the only two things that I want to mention is that, first of all, if you plan to work on this contest, then please use only open source tools, so languages, libraries, packages. And the reason for this is because if you create something interesting, then we would love to share your visualization and your workflow with other researchers as well. And of course, we can only do this with non-commercial, with open source software. And also, winning submissions, so good submissions will be published on this website, in December, January. So please be aware that if you submit something, that your submission may be published under the Creative Commons license. But the main thing that I want to stress is don't be afraid to experiment. So 3D visualization, especially using interactive tools, is a lot of fun. And as you do it, as you play with the data, you learn new techniques, you learn new tools, and it's really interactive, really fun. And don't try to don't be afraid to experiment. And what I'm going to show you today are just suggestions, but this will give you some ideas. But certainly try new things, and would love to have to see new ideas and new techniques. So let's talk about data sets. There are two data sets in this year's competition. Both of them contain Canadian geospatial data. One is from a numerical simulation, and the other one was compiled from several empirical sources. Both data sets are available for downloading right now. So in a few minutes, I'm showing you where you can find them. And both data sets can be analyzed and rendered on a personal computer. So you don't need any HPC, any high-end computing facilities. So basically a laptop with 8 gigabytes or 16 gigabytes of memory will probably be more than enough. But of course, if you want, you can try to visualize these on clusters as well. So the data sets, the first one is a simulation of a storm over Eastern Canada. This one is more difficult because it contains multiple three-dimensional scalar fields. So the data is actually an output of numerical simulation that was run on the Alliance's Narwhal cluster in Quebec. And the data was kindly provided by Alejandro De Luca and François Lauberge from UQAM. So let me just play this movie, and you will see what's going on here. So this movie is actually, it's short because it covers only a few days of the simulation. But as you can see, there's a lot of stuff happening here. So this models a real storm that happened over Halloween in 2019. So the data that I'm sharing with you in the competition covers 3 days from the last day of October until November 2nd, 2019. And in this data set, you have multiple fields, so multiple three-dimensional fields. So the fields are, if I zoom in again, let me try to pause it here. So as you can see, there is a three-dimensional field showing clouds. So there's a cloud layer in the storm. There's rain, so the rain variable. There are ice droplets in the atmosphere. So you can see these are all three-dimensional variables covering the atmosphere. Then there is the logarithm of the snow cover in snow in water equivalent if melted in millimeters. There's also these contours that denote the sea surface level sea pressure. And then there are also projections that show, the mutual, show the mutual distribution of the three-dimensional variables when projected onto two sides of the volume. So a lot of stuff going here. I'm actually going to show you how I did this very quickly in a few minutes. But as you can see, this is a fairly complex data set. So the second data set is simpler. The second data set actually not a numerical simulation. It is what is called the normalized difference vegetation index. So it's a measure of essentially greenness or health of an ecosystem covering the entire province of BC throughout 2022. So there are 53 time steps in this data set. And if I play it back, you see there is just a single variable visualized here. So what you see is this NDVI, normalized difference vegetation index, as animated in time from January 2022 until December 2022 in 53 steps. So this data set is less complex. There are only essentially 2 variables for each data point. And this is also almost two-dimensional data. What I mean by almost is that there's elevation here, but essentially at every surface on at every point on the surface, there is just one data point, which has the geographical coordinates as well as elevation, plus two data variables. So the NDVI index, the measure of greenness, and I'm going to talk to you in a few minutes. A little bit later on, I will describe how this index is measured. And then also its variance. So the variance is essentially, think of it as a standard deviation measured, computed both over space and time. So this data set was kindly provided by Michael Noonan and Stefano Mezzini from the University of British Columbia at Okanagan. So the timeline for the contest is you have 2.5 months roughly before, almost 3 months before the submission deadline. So the deadline is midnight Pacific time, December 10th, so almost 3 months. And then sometime in the second half of December, we're going to review submissions. And then we're going to post the results in early January 2024. And so depending on the results, I'll post some submissions on this website, and we might also do another webinar if we see any, if we see interesting submissions. So for more information, if you go to the website, so if I go to the website of the contest, and there is a contact button here. So please explore the website. To have quick question about the contest, you can use this form. So it's a Google form, just type a question and type your email address as well, so we can get back to you. All communication in the contest, well, apart from quick questions, is going to be via the Google group. So all announcements are going to be via the Google group. So if you're interested in receiving these, please consider joining the Google group. And to join the Google group, all you need to do is just fill in this short form to register your interest, and then we add you to the Google group. And once you're a member of the group, you can post questions, you will receive all communication, etc. So to find information about the data, you can go to the contest website, and in the top menu, by the way, the website is fully bilingual. So if you want to switch to French, there is an option to switch to French, but this webinar is in English, so I'll go back to English. And if you click on data, there are 2 sub-pages. The first one is the STORM dataset. The second one is NDVI index dataset. So let me click on the STORM dataset. And here's the description of the dataset. So basically what we're providing is 3 days worth of data from the numerical simulation. The data are on a 3-dimensional spherical mesh at the horizontal resolution 1060 by 1330 at 16 vertical pressure levels. So keep in mind that the vertical coordinate is actually not elevation, but it's the vertical pressure level. But for visualization purposes, it's actually very, very similar to elevation. So think of this vertical pressure level essentially as elevation. So as you go up, the pressure drops, and there's a pretty much one-to-one correspondence, well, almost, between the 2 variables. So for visualization purposes, the pressure levels can be totally treated as elevation. So all data files are compressed in CDF files, and they can be read. So I'm going to show you actual demos how to read them. They can be read in Python, in ParaView, and with a little bit of data manipulation, you can read them in a Visit program as well. So these are the variables that you can find in this data set. So there are 3 three-dimensional variables. The max mixing ratio of cloud. So what this is essentially it's the cloud, or I guess the water, the water droplets that give rise to clouds. So the max mixing ratio is the mass density of these divided by the mass density of air. So you will see the values, something like 10 to the minus 5, 10 to the minus 4, and so on. The second variable is the mass mixing ratio of rain, and the third one is the max mixing ratio of ice. So these variables are they're all time dependent, right? And also they depend on the pressure, so the vertical coordinate, as well as on 2 horizontal coordinates. So these are latitude and are longitude coordinates, actually rotated coordinates in the rotated grid. So I'm going to show them to you in a couple of minutes. They're not exactly the same as the usual latitude and longitude, but you can go back and forth between the 2 sets of coordinates. And then there are simply 2-dimensional variables. So there is the amount of snow in water equivalent millimeters on the ground, and that's variable I5 inside these 3 files. So each file, there are 3 files here. but each file corresponds to a certain date. So this is October 31st, November 1st, and November 2nd. And the same for three-dimensional variables that I mentioned before. There are 3 netcdf files. So for example, this file will contain these 3 variables for October 31st, 2019. There's also the mean sea level pressure if you want to visualize this. So obviously, this variable is affected by what was happening in the atmosphere by the storm. And there's also, for reference, a couple of topography variables. So there is the land sea mask variable called mg, and there's also elevation variable called me. It's measured in meters. So I'm going to show you how we can actually, in a couple of minutes, how we can actually combine the last 2 variables into a single variable. You don't have to do it, but it's one of the things you can certainly do if you want. So to download the data is linked from this table. So there are about a dozen or so different files. So the total data set files is 1 point something, 1.7, 1.4 gigabytes. So it's not a lot. It can easily fit on your laptop, and you can visualize all of this stuff on your laptop. So you can either click on individual files and just go, for example, like click on this guy, and it opens the web page, and then you can have the download button. If you want to download everything as a batch, if you're in Bash, for example, you can define. So here are a couple of Bash arrays that contain the URLs of these files, and as well as the names, and then you can just run this loop in Bash, and we'll just download the whole thing. So it's going to take, I don't know, a few minutes or a few seconds, depending on your connection speed. So let's talk about loading this data. So I'm going to start with Python first. So to load this data in Python, you need to have 2 things installed. One of them is Xarray, and the other one is a netcdf. And these are fairly standard libraries. So if you use pip, you would install them with pip install Xarray netcdf. If you use Conda on your laptop, then you can find these libraries in the Conda environment as well. So, and then once you install these libraries, you would run something like this. So if you want to load this data in Python. So let me try this. So here I'm going to switch to my shell. And then I'm going to go to the first data set. So these are the files. Actually, let me see how large they are. They are 1.2 gigabytes in total. So here I'm going to start Python. And then I'm just going to import Xarray as XR. So notice that here I'm not importing the netcdf library, but Xarray actually uses netcdf library underneath. So in order to be able to do this, you actually have to have netcdf Python library installed as well. And then I'm going to paste this line. And here the file is in the current directory. So I'm just going to delete the directory path. So it's reading from the current directory. And here I read the data. So what I'm reading is the 3-dimensional data set for October 31st, 2019 with 3 variables, right? And then if I print data, well, actually, if I print type data, it will tell me that it's an Xarray data set. So it's an Xarray data set. Those of you familiar with Xarray library, you will know that inside a data set, you can pack multiple variables. And here you can see multiple variables. So here you see 3-dimensional variables. So this is rain, this is ice, and this is cloud. And then you have also some 2-dimensional and 1-dimensional variables. So the R latitude and R longitude, so these are the variables on top of which the 3-dimensional variables like the cloud lay is defined. You see that here we have R latitude, R longitude. So this is the rotated coordinate system, right? So the way you access this, well, I can simply say data, and then I can say R latitude. So this is going to be a 1-dimensional array, right? So it's a rotated coordinate system on the surface where this is something similar to latitude, but not exactly latitude because it's at an angle, right? So here I have a 1-dimensional rotated array of latitudes, and the same for longitudes. It's a 1-dimensional array, right? But then at each grid point, I have actual longitude and latitudes, right? So these are 2-dimensional arrays that both are defined on top of each R latitude and R longitude match point, right? So to access this, I can do something like this. Data, longitude, for example, and that will give me some information about this. And if I want to access the arrays themselves, I'm going to say values, right? So this is the way, one of the ways you can access values inside the Xarray library. And so this is actually something similar to a NumPy array, right? So in fact, yeah, this is a NumPy array, right? And if I want to access, let's say, a certain value, let's say a value in one of the corners, I'll just do this. Actually, it's a 2-dimensional array, right? So here's a value in one of the corners, but you get the idea, right? Or you can access a subset of an array using the usual Python subsetting notation, right? So this is loading data using the Xarray library. One thing that I also want to mention is time. So we loaded only data for October 31st. So if I print data time, you will see there are 24 time steps. So if I measure the length of this array, there are 24 time steps, but each day contains hourly data. So there are 24 times 372 time steps in total for if you create the entire visualization, right? So alternatively, in Python, you can read data using the netcdf Python interface. And the way you do this is, well, just load the netcdf library, and then you load the file. So again, in my case, it's sitting in my current directory. So I'm loading the three-dimensional volumetric data set in Python. And so here I have the data, right? So I can just print the data and I can access, various variables using this notation. So in netcdf, it's slightly different from Xarray. So for example, here's how I would access data for the cloud variable, right? So here's the data with this horizontal resolution, this many time steps for the single day, this number of vertical pressure levels, right? And to actually access the data, you can do something like this, right? And that will give you access to a three-dimensional NumPy array. So actually, Python is processing this large array, but you get the idea, all right? So let me jump to ParaView, which is much more interesting because it's visual. So to load data into ParaView, you would simply point to netcdf files. So let me go back to my notes, and let's try to recreate. So I'm going to recreate the complete workflow that you saw in the animation before. So this workflow for me is actually saved inside, oops, let me go back to this directory, is saved inside these state files. So I'm not sharing the state file on purpose because I want you to create something different, right? I don't want to recreate my exact visualization. I want you to come up with some new visualization, but I'm just going to show you how you can actually create a visualization step by step using using this approach in ParaView. So I'm going to start ParaView. Oops, not that. ParaView 5.11, the most recent version of ParaView. Here it is. And then I'm gonna go to File, Load State, and then I'm gonna navigate to this file, A014. So as you can see from the numbering, it's actually the 14th version of my full visualization workflow for this data set. So I guess I'm gonna say, okay, I'm gonna take a couple of seconds to load it. And here you can see the visualization. So what you saw in the movie before, right? So it's actually a three-dimensional visualization, right? And there are many, many objects here. So think of them as layers. So here in the pipeline, there are many objects. And let me turn off some of the objects that are kind of obvious. So here I have the contour level that I'm turning on and off. So this is for the surface level sea pressure, right? So I'm going to turn it off. There are a couple of annotations. So for so this pressure range corresponds roughly to the vertical to the elevation range from 0 to 16 kilometers. So I'm going to turn off these labels, 0 and 16 kilometers. Next, I'm going to turn off the topography. So the topography is, I'm going to talk about it in a few minutes in more detail, is given in this variable. Next, I'm going to turn off the logarithm of the snow level in water equivalent in millimeters right here. I'm going to turn it off. And now what, what I have is only three-dimensional variables, right? So now I'm looking at clouds, rain, and ice. And as you can see, I also have projections of these three-dimensional variables onto the two sides of the volume. So let me turn off these projections. So these projections actually created using a programmable filter. So I'm going to turn off, I'm just simplifying my view, turn off these projections. So now what you see are just the three-dimensional distribution of variables for clouds, rain, and ice. And as you can see, I use different techniques for visualizing this. So if you look at, so you can see things that are visible right now is the cloud layer right here. So you're turning it off and off, on and off. So the cloud layer is visualized using the volumetric projection, right? So think of the volumetric projection as ray tracing through the volume with some transfer function, right? So here I'm using the volumetric representation for the cloud layer. Whereas for the rain and the ice, I'm using contours. So here I have the rain, right? So it's a contour at a given level of, well, at a certain level of the rain variable, and the same for the ice. So here I can turn it on and off, and it's visualized as a contour, as a three-dimensional well, isosurface, right? So the reason I did this is because if you were to visualize, let's say, all three variables as using volumetric representation, you will run into a lot of problems because it will be very difficult to distinguish between them visually. Okay? All right. So let me show how we can actually manipulate these variables. So I showed you the final result. Let me reset peer review. And next, I'm actually going to show you how I do this in reverse order, starting from scratch. So I'm going to talk about the flat topography file. So what I'm going to do is I'm going to load a couple of variables. One of them is the land sea mask mg. So it's a two-dimensional variable from this file. So this is one of the files available in this data set. And then I'm also going to load the topographical elevation in meters from this file. All right. So I'm going to show, going to go to File, Open, and then navigate to the data set. So the first one, land sea mask mg from PM all zeros file. So from this file, I'm going to say, OK, it's a netcdf file. So I'm loading it as, well, using the generic netcdf reader. All right, hit Apply. And when it's loaded, you see that I actually have this data on a spherical mesh, right? So the spherical mesh, if I go to information, you see that it has dimensions 1330 by 1060. So these are the horizontal dimensions. And then the vertical dimension is 0 to 0. So it's just one, essentially 1 point, right? So it's a two-dimensional data set. Even though we're looking at it in 3D, this is a two-dimensional variable. And the variable that we're interested in is the land sea mask. So it's called mg. And it goes from, well, it's either 0 or 1, right? So if it's, I guess, if it's land, then it's 1. If it's sea, then it's 0. Water, sea or lake, then it's 0. Okay, so if I visualize it, if I go to surface representation, and then visualize the image variable, this is what it looks like, right? So 0 corresponds to water, and then 1 corresponds to land. As you can see, if you zoom in, there are lots of small lakes in, around the Great Lakes and near Hudson Bay. All right, great. So the second variable I'm going to load from a different file. I'm going to load the topographical elevation. So this time I'll be looking at the file called dm and then all zeros. So it's a time-independent file. I'm going to use the same netcdf reader. And now the variable I'm going to show is going to be called me. So me is a smooth variable that is simply elevation in meters. So for water, it's obviously 0, right? And then it goes up to 1,500 or so meters in this region, right? So here I have completely two different files, completely two different variables, right? And as you can see right now, I can visualize either one or the other, but not both of them. So in peer review, it's actually possible to append these variables to create a single variable. So the way I do this, I'm going to highlight both data sets in the pipeline browser, and then I'm going to go to Filters, Search, and I'm going to search for Append Attributes filter, Append Attributes, and then I'm just going to click Apply. And what it does, it creates a new discretization onto which both variables are projected, right? So right now in this new discretization, so not right now, I'm looking only at the output of the append filter. Now I have two variables. I have now mg variable, which is the land sea mask, is either 0 or 1. And then I have the me variable, which is the elevation in meters. And then I'm going to the output of this append filter, I'm going to apply the calculated filter, and then I'm going to create a new variable that I'm going to call elevation. So elevation is simply the product of the land sea mask and the actual elevation, mg times me, right? So when I do this, I get a new variable called elevation, right? And this new variable, as you can see, is nice because I can actually apply a threshold filter to it. So a threshold filter, and then I can exclude everything, let's say above 1 meter, below 1 meter. I'm going to say apply. And this way I actually have, the elevation in this data set, as well as the land sea mask, right? And everything is encoded in a single variable, which could be useful, right? And then now what I'm going to do is, right now you're looking at the visualization in spherical geometry, and I'm going to make it flat. And so the reason why I'm making it flat is you will see in a few minutes, it actually to speed up rendering of 3D variables. But to make it flat, you need to apply the programmable filter. So what a programmable filter does, it will create a totally new discretization unrelated to the previous discretizations, and then it will simply take my existing elevation variable, which is currently a two-dimensional variable, and put that onto a new discretization. So what I'm going to do is I'm going to click on threshold, and then I'm going to go to filters, search, and then search for a filter called programmable filter. And then inside the programmable filter, I'm going to create a new, I'm going to create a new discretization of type VTK image data. So VTK image data means Cartesian mesh in VTK language. So I'm creating a new Cartesian mesh. And the way I do this, I'm copying, so from the notes, today's notes, I'm going to copy the following code. So here I'm copying the following code. And what it does here is it simply takes the input. So the input to the programmable filter is the output of my threshold filter, right? So I'm taking the input, and from this input, I'm looking at the elevation variable, and then I'm going to assign it to a new VTK variable called elevation, right? And then I'm also setting, so for the output, my output is going to be a Cartesian mesh, because here I specify the data set type as VTK image data, so the output is Cartesian mesh. And then here I'm specifying the properties of this Cartesian mesh. So I'm putting the origin as 0, 0, 0. Spacing could be, well, not anything, but you can play with it. So you could use 1, 1, 1. I use 1, 1, 3. And then you specify dimensions as well as extent. So these are taken from this ext variable. And in fact, let me actually just print this ext variable. So you will see what it looks like. So I print ext variable, and then I apply the filter. Oops, why did it complain? Okay, so maybe I'll need to apply let me apply the programmable filter to the output, not of the threshold, but yeah, the calculator. So that'll be easy. Yeah, I think that will work. So I delete the threshold. I will apply threshold later on. And then I will apply the programmable filter to the output of the calculator filter. So here I'm going to create a Cartesian mesh, VTK image data, into which I'm going to paste my code. And then here, what I want to do to show you the extent variable, so I'm going to say print extent. I think this will work. Yeah, excellent. So this works, great. And I want to show you the output. So here I have output messages, and then, yeah, so here's what extent looks like, right? So basically, in 3 dimensions, the first dimension goes from 0 to 1329. Second one goes from 0 to 1059. So these are, 1330 by 1060 is the horizontal size of my data set. And then in third dimension, there's nothing. Well, it's just one data point, right? So one layer. So it's a 2-dimensional data set. But I'm projecting this onto a Cartesian mesh. And the reasons for this will become clearer in a few minutes, right? So here I have the output, which is essentially, a Cartesian mesh. Let me see. Here's a Cartesian mesh, right? And here what I'm looking is at the actually elevation variable, like this. So here you can see Newfoundland. Here you can see Nova Scotia, the Great Lakes, and so on. And now I can actually apply probably the threshold filter when I'm going to delete everything below elevation of 1 meter, right? And then so here you have a nice visualization, flat geometry. And then if you want to save this data set, you can go to File, Save Data. And then I can save this data set at, let's say, topo.pvd. So PVD stands for ParaView data. So it's just basically one of the intrinsic file formats in ParaView, right? And then the nice thing is that later on, so let's say I want to refresh ParaView, I go to File, Open, and then I can load this topo.pvd file, and then here it is. So I don't have to go through everything I've gone through before. All right. So here's how you would project the topography to 2D and write it out as a separate file. So now you can visualize everything in 3D. So let's try to load one of the 3-dimensional files and then visualize the cloud layer. So I'm going to load a three-dimensional file. So I'm going to load one of the files, DP files, one of these guys, so October 31st, and then using the netcdf reader. So here you can see that if I load it, what I get is the spherical wedge. And the reason for this is because, well, I didn't tell Preview that I don't want to go in spherical coordinates from the very center of the Earth. So to rectify that, you want to have a non-zero vertical bias. I'm going to set it to 10,000, and then I'm going to say apply again. And then here what I have, right? So here, while looking at, I want to call it by the cloud variable, right? So you have the cloud variable. And the problem here is that if you're looking at the outer surface, then it's just not interesting, right? And obviously there's something happening, so there's a little cloud layer, but there's not much you can see here just looking at the outer surface of the data set. So one thing you could do is you can go to volumetric view. So if I go to volume view, then unfortunately, right now is doing ray tracing in spherical geometry, and that will take a while, maybe 20, maybe 40 seconds, right? So ray tracing, volumetric view is essentially ray tracing through the volume, and ray tracing in spherical, in curved geometries takes a very long time in general, right? So this is the reason why I suggest that instead of visualizing this data in spherical geometry, you actually transform it to a flat geometry, to Cartesian mesh, and then ray tracing will just take a small fraction of a second, right? So I'm running this in parallel with Zoom, so it might actually take even longer than half a minute. But the point here is that if you try to visualize the cloud layer in 3D using spherical geometry, it's going to take a while. So let me just wait. I hope it'll finish very soon. Yeah, maybe I should just kill it because it's taking a while. So let me just kill this. I'll kill Paraview and I'll start Paraview. So killing Paraview, and then I will start Paraview from scratch. So let's reload the data. And then let's convert it to a flat Cartesian geometry. So inside data one, I'm going to read one of these three-dimensional files, October 31st, netcdf freedom, and then using the vertical bias of 10,000. So here it is, right? And then straight away, I'm going to apply the programmable filter to it. So the programmable filter, then the output is going to be VTK image data, so Cartesian mesh. And then what I'm going to do is I will take one of the variables. I'm going to take the rain variable. So right here, I have the rain variable. And then I'm going to put it onto a three-dimensional Cartesian mesh. So here's my rain variable. And then the mesh is going to have, this origin, three-dimensional mesh, this spacing 119. Actually, let me change it to 111. And then here are the dimensions, the extent. And then on this mesh, I define the rain variable right here. So I set the name and also set the scalar. So the scalar comes from VTK data array, which actually set by this line, right? So here I take my rain variable right here that I read from the spherical geometry input file, and then I'm porting it onto a Cartesian mesh. So when I do this, what will happen is you will get a new three-dimensional mesh. And as you can see, it's very flat because there are, some like 1,300 by 1,000 horizontal points and only 16 points in the vertical direction, right? So what I want to do is you actually want to increase the extent in the vertical direction. And there are many ways of doing this. So one of the ways is where you set spacing. I'm going to set it to 119 to make it thicker in the vertical direction, right? So here I have my three-dimensional mesh. And on this mesh, I have the rain variable. So if I look at the outer surface, here's my rain variable. Again, it's kind of boring, right? But what I can do now is you can go to volumetric view. And now, as you can see, volumetric view is really fast. So here we're looking at the rain variable. Let me also show the outline. Oops. Of my volume. Let's see. Yeah, right now it'll be difficult to show the outline. Well, never mind about the outline. So here I have my my three-dimensional variable that I can actually color because it's let's say it's rain. Let's color it using a green palette. So here I go to edit color map, then switch to a different color, and then let's just pick up a color which is more green, as in my previous visualization. I don't know, so something like this maybe, right? And so here you get the idea, right? So you have a green layer. If you want to visualize it not using the volume representation, but using the surface representation, let me go back to surface representation. What you can do, you can also apply a contour filter. So a set of isosurfaces where instead of a single value, I'm going to have, let's say, 10 values on a logarithmic scale. So I'm looking at the rain variable. I'm drawing 10 isosurfaces on a logarithmic scale from an absolute minimum to absolute maximum. I'm going to say generate, and that, oh, hit apply, and that's generating 10 isosurfaces, and this is what it looks like, right? So here, just to give an idea of how you can visualize the rain variable. Of course, in addition to the rain variable, there are also the cloud variable, as well as the ice droplets in the atmosphere variable, right? So there are three-dimensional variables. Okay, so are there any questions at this point? So last thing I want to show you is how we can do time stepping, and then I will jump to the second data set. So this is so here we're loaded one of the three files. So this file is for October 31st, and it has 24 time steps, right? So hourly data. Let's see if I can actually show it here. Maybe the contour filter didn't apply. Let me see. Look at this guy. Oops, sorry, information panel. This guy, yeah. So here we have 24 time steps, right? And let's just show this back again as a volume. So here I have 24 time steps. And then if you want to play them back, of course, in Preview, you can simply hit the playback button, right? So this will, it takes, I don't know, a fraction, half a second to render each frame. So as you can see, it's rendering live, and it's showing these images for each of the 24 time steps. So I'm going to pause this. Then if you want to save this, you can go to File, Save Animation, and then you want to save as a PNG file format. So save these 24 images as PNG files, and then you can use a tool like FFmpeg to merge these into sort of a famous, very popular command line utility called FFmpeg, which is linked from the notes. They can use to merge these individual frames into a movie, let's say 10 frames per second. I prefer a different approach because it lets me script everything. So what I do here is I actually go to my visualization. So let's say this visualization, and then I save this visualization as a Python state file. So go to File, Save State, File, Save State, and let's say I want to call it anim1d Python, right? So in this directory, that's what I'm going to call it. I'm going to save it as a Python script, not as a PVSM preview state machine file, but as a Python script. So here I have the Python script that corresponds to this visualization. And then what I do next is I can open this file inside a text editor. So let me bring my text editor here. So I'm going to open, open the file documents. Actually, let me show it here. So it's going to be anim1d. So I'm going to open the script. And then here you can look for the line where I'm reading, actually loading the data. So look for the line netcdf reader, netcdf, search for the line in this Python script netcdf reader. And so here what I'm going to do is, to simplify things, I'm going to replace this output, so this variable name with, replace this with just data, right? So there are just a few occurrences of this data, great. And then towards the end, what I'm going to do is I'm going to paste these lines. So these lines, let me step through all time steps inside a single netcdf file. So I'm loading this data into a variable. So where's my netcdf reader? Into a variable called data. And this variable has many attributes. One of them is dot time step values. So time step values, which actually contain, a list of 24 time steps. And then you can actually cycle through these time steps. And then at each iteration loop, you can update your pipeline. So load new data from the new time step, and then you can update your view, right? So render the new time step. And then here you save the screenshot. So obviously you need to specify the path, right? And then when you run these as a script, so you can run scripts in Preview using, for example, PyPython. You can do it from the GUI as well. So if you're not sure how to do it, then unfortunately, I don't have time to show this now. But you can consult documentation. There are many, many ways of running a script, right? And so when you run the script, you actually, for example, using PyPython, it will take a few seconds, and then at the end, you will have 24 PNG files, and then you can merge them into a movie. So the challenge here is really to visualize multiple three-dimensional fields and their relative positions. So it's difficult to do because they are overlapping fields. But if you want to, so here we have some suggestions. If you go to tasks in the contest website, here are some suggestions we have. So, things you can do. But now I'm going to go to the second data set. And so because we have only 10 minutes left. So an DVI index over BC. And this data was provided by the research group from UBC Okanagan. So here we have data covering, actually, let me go to here to data, and then in description of NVDI data set. So here we have data containing the so-called NDVI, Normalized Difference Vegetation Index, which is measured by remote sensing, so usually from satellites, but sometimes from high aircraft as well. So what this index measures is the amount of greenness. So it goes from -1 to +1, right? So it's basically the ratio of reflectivity in two bands, the infrared band and the red band. And this ratio, as you can see, can go from -1 to +1. But basically, if it's close to +1, it means very dense vegetation, like dense forest canopy in the Amazon. So normally for BC rainforest, it'll be somewhere in the region between 0.6 and 0.8. If you have sparse vegetation, then it's going to be something like 0.2, 0.3. If you have just dry land with no vegetation, it'll be close to 0, just above 0. Then snow, glaciers, clouds will give you small negative values, and then have open water. Typically, that value of reflectivity is close to -1. And what's interesting in this data set is that in addition to this NDVI index, it also gives you the variance. So the variance just tells you how fast this index changes both in space and time. And so the idea is, again, if you go to tasks, here we have some ideas, some suggestions of what things you can visualize. So read through these suggestions, right? But right now, I'm just going to show you how we can load this data set. So first in Python, you can, oops, sorry. Yeah, that's the right data set. So in Python, so here we're provided in two formats. Both formats are self-sufficient, so just pick up the format you like. They're quite different from each other. So one is a VTK format, the other one is a compressed CSV format. So in a compressed CSV format, we have 53 files, so 53 time steps. A single time step is a separate file. And then in the CSV format, each line is a data point. So these data points are not connected. They do not form any sort of mesh. They're just individual data points. And then each data point contains a number of variables. So for the compressed CSV file, the variables are longitude, latitude, elevation in kilometers for each data point, two horizontal coordinates in the Albus conic projection. So this projection is nice because it gives you equal, areas of equal size it will have equal size in the visualization in this projection, as well as two actual data variables. So the NDVI index mu and its variance sigma 2. So when you load this compressed CSV file, you will get a large data frame, and then each row is going to be a point, so each column is going to be a variable, right? And to load this CSV file, so here we have an example, very easy to read. You don't even have to unpack the CSV file. So here, if I go, let me drag my text editor. If I go to the data, let's say I go to data 2, oops. So here I go to the CSV file format, and then let me start Python. And then I'm just going to paste these lines to read this data using pandas. So it's a CSV file. So data will take a few seconds to read. And if I inquire about the shape, so this file, this single time step, first time step, contains almost 6 million lines. There are 6 million data points. And then there are 7 variables that I just mentioned, right? So the variables, if you list the columns, these are the variables that are contained in this file. So the second file format, VTK file format, has the same data, but in a different format. So the nice thing about this is VTK file format is a format that was created by folks who created ParaView. And so these data you can load easily into ParaView because what you have here is essentially a set of points, a set of three-dimensional points. And each point has several variables stored on top of it. So you have the mean NDVI index, the variance, as well as elevation in kilometers. So let me show you how to load this inside ParaView. I'm going to restart ParaView from scratch. And then I'm going to go to File Open. And then instead of data 1, data 2, so VTK file format. And here I'm loading the first time step. I'm going to say Apply. And then when I load it, nothing shows up here, right? And the reason for this is because what you loaded 6 million data points. So here are 6 million, almost 6 million data points, right? And these are the variables that are stored on top of data points, so elevation, mu, and sigma 2. But the data points are infinitely small, so you don't see them. So what you can do is a number of things. One thing you can do is you can switch from a surface or point representation to a point Gaussian representation. And what it does, point Gaussian representation, it places a glyph, in this case, a sphere on top of each data point, right? Looks kind of strange, but if you scroll in the properties, if you scroll down, then, so here where I have the point Gaussian representation, right here, I will reduce the size of these dots, of these spheres. And then for shader preset, I'm going to go from sphere to a plane circle, right? So here, and then I can color it by, for example, by the mu variable. So here's my NDVI index, and you can see it's a three-dimensional data set. So if I zoom in on this, you can see that these are individual data points. So let me make them smaller. Yeah, so these are individual data points, right? So not particularly interesting, but when you zoom out, it gives you a nice picture. And if you inspect the data closely, we'll see there are some artifacts, and these artifacts, for example, these data points, there are a few other data points. They come from the numerical fit, and they should not really affect your visualization, but you might discover some artifacts, and I'm aware of this. So please, you can exclude them if you want, or you can just neglect them. They should not really affect your visualization. All right. And one thing that I want to point out is that normally the NDVI index is displayed in a color map that goes from dark colors, from brown to green. So green means dense vegetation. And on the website, actually provide these color maps. So if you scroll down in the data description page, there is a link to the color map. And then this color map, I'm going to show you what it looks like in ParaView. So here, I just loaded previously. So here's this color map, which is stored as a JSON file. And then here I apply it. And this is what the vegetation index, this index looks like in this color map, right? So it goes from essentially, oh, actually, I have to also specify one thing that I forgot to do is I have to specify a custom range because I want this color map to cover the range from -1 to 1. So here, and then here I have data for the first time step. So it's in early January 2022, and there's not much vegetation. So as you can see, if I go to, let's say, oh, I have just the first time step loaded. But if I go to a later time step, then I will get a lot more green color, right? And in fact, let me actually play a simple animation that I created before this workshop. So let's see this animation that shows both variables side by side. So here I'm cycling through the year, right? So on the left you have the NDVI index, and then on the right you have its variance. So this is what they look like. And what I want you to visualize is, well, come up with some interesting visualizations, some interesting ideas. One suggestion I have, you can do a flyover above BC, right? So maybe focus on some geographical regions and then fly over BC, or the sky is really the limit. So don't be afraid to experiment and try new things. So all right, so we're out of time. We have only 4 minutes left, and I think I will just open the floor for questions.